and he will detail their advantages and the potential of applications. Julien, the floor is yours.
Thank you, Sophie. Yes, so this work has been done with a colleague from Renault within the context of Civalab joint laboratory between UTC, CNRS and Renault. So here I will, it will be like a very simple tutorial about different cameras. Why? Because we use a lot the RGB camera for the automotive, and it has some limits, especially in adverse weather conditions. So here, this overview is for autonomous driving or as well for ADAS. So, firstly, I will briefly explain what is light and what are the characteristics of the light, and then I will explain step by step different sensors. Starting by the standard cameras, and then I will present two infrared cameras, and then the range-gated camera, polarization camera, and finally the event camera. So what is light? Light is an electromagnetic wave, so it propagates in a specific way, and it has an electric oscillation and associated with a magnetic oscillation. The most used characteristic is the amplitude. In fact, it is what we measure with the sensors. The wavelength, so it will have, that will give, for example, the colors, and the sensors will be sensitive to specific wavelengths of the spectrum. And there is another characteristic, the polarization, which is the oscillation angle or orientation. And so when we speak about adverse weather, it can be for rain, fog. An important characteristic is that the longer are the wavelengths, the better they penetrate the atmospheric fog, for example. So here we have also so the full electromagnetic spectrum in the top, and the visible light is only a small part of it, from 400 to 700 nanometers. And just after that, you have the infrared part, which can be divided in different slices: near infrared, short wavelength infrared, medium infrared, etc., up to long wavelength infrared. So here I will focus only on near infrared and long wavelength infrared. And the last figure in the bottom is the solar spectrum distribution. This is what gives the sun to us. So the yellow is on the top of atmosphere, and the red graph is what we have on the ground, because the atmosphere will filter some of the frequencies. So, as I told before, the visible light is only a small part of the spectrum, and it is only 40% of the solar radiation also. So we see just a partial, we have just a partial vision of what we could do. So maybe sensors can be better than human eyes. For near infrared is wider and it is longer, so we may hope it will better penetrate atmosphere and fog, for example. And we can note here the green square is the spectrum window. That means in the ground we don't have this wavelength, so we can use them for active sensors, for example. It can be advantageous to use it because it will not disturb the natural enlightenment. So how to capture the light? We need specific materials put into a sensor with a semiconductor photodiodes to catch the photons, to convert them to electrons according to the intensity of the light. So the most common one is made of silicon. This is what we use to make the CMOS sensors for the RGB and it's widely available, so we can do cheap cameras. So here we have the sensitivity response of the silicon, which is good for visible spectrum, as well as the first part of near-infrared. So it will be good to make near-infrared cameras also. Now, if we want to get longer wavelength, we will use different materials. Here we have the germanium and indium gallium arsenide that are sensitive to near-infrared and the beginning of the short wavelength infrared. So we can use them. They are less common because it is more expensive to build. So about a camera, what can we do with a camera? So the source is the light. So we have emitted light from the sun, which is transformed by the atmosphere with specific scattering. So we have scattered light coming to the object. For example, the car, a road. The car can have a very specular reflection, whereas the road will be very diffuse. So this reflected light will go to the camera lens, and then, so we have full spectrum. The sensor is made of silicon, so it will be sensitive to visible spectrum as well as near-infrared. So we add a near-infrared cutoff filter to remove it, and then we have a color filter array, typically Bayer filter, to generate, to give a color to each photoset, and then to generate RGB images through image signal processing. So we have this pipeline to get an image, and then what can we do? We use this image in a perception system, so we have very strong algorithms. So the RGB camera is widely used, and now it works well because we have a lot of data and we have very good algorithms. That's not the case for the other modalities. So RGB camera still has advanced thanks to the research that has been done before to process RGB. So we can imagine different applications such as object detection. So the RGB camera is very versatile. We can use it for many applications. It outputs the colors that is good. It is rich information. We can see the texture, we can see many different things thanks to the color. We can integrate it behind the windshield, for example, such as a Mobileye camera, usually on top of the windshield. And it's very cheap now because we manufacture a lot of RGB cameras. However, it works well in good conditions. You will have very strong degradations at night or under adverse conditions. So, for example, if you have the sun in the front of you, you can have glare or blooming, and you can have reflections on the ground. When you are typically close to the exit of a tunnel, you will have a very high contrast, so you will not be able to see everything. You will have to choose if you see what is in the dark side or in the bright side. So the camera will not know how to do its exposure. And if you have typically fog, you will not see very far because the RGB light will not penetrate the fog. So we can use first, so it is a common camera, it's a near-infrared camera. Near-infrared camera is easy to do because we can use the same sensor made of silicon. Here is, so we can switch easily by changing the filter we put. So instead of filtering the infrared, we can remove the RGB, for example, and then we get a near-infrared camera. Here, it's an Omnivision RGB IR sensor that will try to get all this information, so simultaneously color and near-infrared. So they propose to use a pixel array filter made of blue, green, red, and infrared filters. This way they can process to adapt their camera to do day vision with color data and night vision by using near infrared associated with an illuminator. So as you can see, the scene in colors and with near infrared modality. So near infrared cameras are used, for example, for driver monitoring systems because we can illuminate the scene with near infrared light. We don't see it, so it will not disturb the driver, and it allows to have always a good illumination of the face of the driver. A common usage is also what we call night vision, so we will, associated with good illumination, we will see at night without disturbing the other drivers, for example. So you have an illustration here, so it will give you grayscale image that you will process in a similar way that you process color image. You don't have, so you can see still the lane markings, the traffic signs on the road, and it is cheap as well as the RGB camera. However, it has not so much advantages for blooming and bad weather. So we will see other sensors with other characteristics. Here I present the thermal camera. In fact, thermal camera is based on long wavelength infrared. So the thermal camera will measure the height of the bodies. Here you have the example of the pedestrian that gives a specific radiation at 12 micrometers, which is located in the long wavelength infrared band. So you have two different technologies of thermal cameras. The one which is similar to the classic sensors, which will convert photons to electrons, but this camera needs to be cooled a lot because there will be interference with its own the heat generated by the electronics of the camera itself. So it must be very, very cold. So it is very expensive and you can use only for very specific applications. So if you want a small thermal camera, you will use another technology. Usually we call them uncooled thermal camera, made of the sensor is in fact an array of microbolometers that will measure the wavelengths and transfer it to electrons. We can do it because we know, for example, the pedestrian body will give you a wavelength around 12 micrometers, and you can recover the temperature this way. So here we are in the long wavelength infrared. There is we don't use a standard lens made of glass. The glass will be opaque for long wavelength infrared. So we need to use a specific lens material, usually the germanium, which is transparent for this wavelength. And to our eyes, it is opaque. It is dark, in fact, when we look at such a lens. And the drawback caused by this fact is we cannot integrate the thermal camera behind the windshield of the car. But we can put it in another place, for example, like the Audi illustration. So the thermal camera is good because we don't need any illuminator. It just related to the body's heat temperature. We can detect, we have a far detection range compared to near infrared, for example, it's twice better. And it has a good penetration in the atmosphere, even if in case of adverse conditions. So we can use it at night, and in foggy day, it will be very reliable in this case. But it's still expensive compared to the other cameras. And in fact, we see very well the warm bodies, such as pedestrians and animals. So it is perfect for these applications, but not good, for example, to detect traffic signs, lane markings, etc., we will not see them in the thermal modality. Now, another kind of sensor with other qualities, it is a range-gated camera. So this is a camera with a relation to the depth. So the idea is to have an illuminator, for example, near infrared. You will emit the light, and then we will choose when to expose the image. So we will first emit the light, and then we will shutter, we will expose a small time, so a specific gate of time, and it will, according to the time, the travel time of the light from an obstacle to come back to the camera, we have a relation according to a range. So we can choose, by choosing, we can expose different gates at once with the same camera, and we can choose at which distance we want to see something. So the idea, the big advantage is that we don't see the scattering caused by atmospheric adverse conditions. So it is the big quality of the range-gated camera, so you can see through the fog and see very well after that. And you can, the other big advantage is you have depth information, and you can choose at which depth you would like to see. So it is good for adverse conditions. However, the difficulty is to synchronize very accurately the illuminator and the camera to treat it when we want. Another kind of camera is polarization camera. So the light is usually, transmitted light is unpolarized, so you have vibrations in all the directions, but the angle of the polarization can be used to filter the light. And it occurs especially when you have some reflections on specific body, especially the very specular reflections. And you can filter the light thanks to this characteristic, and you can get robustness to specific glare, to specific reflections. So, at the right illustration is a new Sony sensor, PRGB sensor, which has the Bayer array and a polarizer array in different directions, different angles of polarization to filter to keep only specific angles, and then we can fuse the information to get the best view we can. So the applications currently, this is not the most common sensor, so you have not so much work about it. So we can see currently it as an enhancement for standard image, standard vision. For example, here we can reconstruct high dynamic range image thanks to this characteristic, to the polarized characteristics. So it allows to have a better robustness to adverse conditions, adverse weather, and to improve classic vision algorithms because we have a better entry point. So it is still in study. You have different representations for the polarization features, and still it is not perfect. It can be still sensible to blooming and very difficult weather. Now the last new sensor is the event camera. So this camera is a different idea. So instead of taking a picture at a specific frame rate in a discrete time, so normal picture you have a dense frame at a specific frame rate. Event camera will be a continuous flow of the intensity changes. In fact, the idea is to imitate the A cells, and the A cells will send some impulsions when they detect a light change. that can be positive or negative. So here we will have pixels that are independent and asynchronous, and they will emit a pulse for every change they detect, and it will be a continuous flow of change. So you will have X, Y direction, as well as the time. The time will be very important for event camera. So instead of having frames, you will have events. And then for illustration, we can accumulate the events to show frame-like representation. Usually we see specifically the edge of the elements. So it doesn't need it has a very big dynamic because it works only by measuring the light differences. So it has a widely better dynamics than a standard camera, even HDR camera. It can work at night, and it is very fast. It has a microsecond temporal response that allow a very low latency, and it needs less power than a comparable RGB camera. So the disadvantages are difficulties to process more than disadvantage. So the events are sparse in space. Still, we have to leverage some challenges in the processing. You see, you can imagine it measures, it perceives the motion. So if there is no motion, it sees nothing. So if you don't move and if the scene nothing is moving, you will not see anything. And you can see, for example, undesired events. For example, you have strong shadows, you will see them also. If you move, you will see also the shadows, but you don't want to see them because, for example, if you have shadows on the road, you will not stop, you will continue. So you can use them for detection applications as well as for example, driving monitoring system. Here in this illustration, we can see through the dark glass. And the tunnel illustration here, we can see everything, whereas the standard camera has a strong blooming effect. So to conclude, is a simplicity table. So it is very simple. So it's just to have an overview of the sensors and so the advantages they can have and the applications they currently have. So maybe some points, maybe it can evolve according to the progress that will be done in the future. Thank you.